Okay, so we're going to start with a more quantitative understanding of electrostatics now as we go through electrostatic force in our third lecture here. So I can describe what happens when two objects are near each other. Two charged objects, I apologize. When two charged objects are near each other. So we talked about this a lot already with some of the diagrams that we had. When the if two things are or two things have the same charge, they're going to repel. If two things have opposite charges, they will attract. Okay. I could define electric force, so you'll notice that electric force is going to look very similar to your equation for gravitational force, and we'll talk about that a bunch when we actually get to that equation. I could state Coulomb's law and its purpose. So Coulomb's law is going to be bit for electrostatic force, being able to calculate it, and we'll kind of talk about how he came up with that. I can relate electric force to other forces that I know about. So as I said, electric force is going to actually look quite a bit like gravitational force in terms of its form. Just looking for my pen here. So we remember the gravitational force is equal to this. So you'll notice that when we do Coulomb's law, or the equation for electric force, it will have a similar form to this. Okay, so I know we haven't actually done the demonstrations yet just because the timing hasn't been perfect for this, but I'm going to show you the video of the paper bits getting attracted by something that has a negative charge, and we will still do it in class. I just want to make sure that we actually are able to see what's going on here. Okay, so like I said, we haven't done it in class, but we will. So we talked about the word polarization already, so hopefully that helps to actually put it in some kind of visual context here. So when A gets brought towards B, the electrons in A are going to get repelled, and so this is what you kind of see happening over here. So you have a neutral rod and a stationary negatively charged object here. Okay, so rod A and rod B. The electrons in A are going to move to the left side, as you can see here, and that causes the left and right sides of the rod to basically have a different charge. Overall, you could see that there are still equal amounts of negative and positive charge, but what is polarized here is the fact that all of the negative is on the left and all of the positive charge is on the right, and that's what the idea of being polarized is, such that the positive net charge on the right side of A is then going to move towards B because opposites are going to attract. So you can see that, once again, B is not polarized right now, but the positive charges along the rod A are going to be attracted to rod B. So, what is going to happen if a neutral rod is brought near a a negatively charged rod? So you can see that the rods would feel an attractive force because they are going to be, because of what I just said with the polarization in terms of the fact that all of the negative charges are going to move toward the left and the positive charges are going to move toward the right. Okay, so we took care of that question. Now our next question here, what happens to the electrons in a neutral conductor that is brought close to a positively charged rod? So if we think about this, it's very, very similar to our previous question of, okay, if I have a neutral conductor here, such that, let me do this with my pen instead of my mouse, such that you have, remember that it's going to get polarized when a rod is brought next to it. So let's say that it looks like that, because if I am going to have a positively charged rod, that rod is going to be on this side such that the electrons are actually attracted to it. So your answer to this question should be that the electrons are going to move to the side of the conductor that is next to the positive rod, because once again, the electrons are going to be attracted to positive particles or positive charge. Okay. So we know that Newton's first law states that objects that are moving at a certain velocity are going to maintain that velocity unless acted upon by an external force. If you remember, that's the law of inertia. So the free rod accelerated towards the stationary rod in a situation where we have, once again, we have a polarized rod here and a negatively charged rod here, such that this rod on the left is going to physically move toward the rod on the right. That means that there must be a force present, and we call that the electric force. Okay. So in the 18th century, Joseph Priestley reasoned that John Robison measured the force between two objects, followed the same principles as the gravitational force. Okay, so the force between two objects that are charged depends on an inverse square law in the same way that two objects that have mass has been dependent on an inverse square law. So Fe is proportional to 1 over r squared. So then this guy, Charles Coulomb, again, who the law is actually named after, publishes a paper based on detailed experiments that definitively proved Priestley and Robison's work, so that the force was also proportional to the size of the charges, and we'll talk about that. So he used what's called the torsion balance, which is based on the same principle as Cavendish's experiment that was able to measure the gravitational constant. So I'll show you what this looks like. I realized that the audio wasn't playing in that about a minute in, so I'm gonna hope that it works and try this again.
Measured the magnitudes of the electric forces between charged objects using the torsion balance which he invented. Coulomb's torsion balance is an instrument that enables us to verify experimentally the quantitative law of interaction between electrical charges. Coulomb's torsion balance consists of a cylindrical or square glass case closed by a lid. A glass tube emerges from the lid. The tube is closed with a piece of metal called torsion head. A torsion fiber is suspended from the torsion head. This fiber holds a horizontal needle made of lac with a small brass disc at one end and a sphere of elder pith at the other. The height of the needle is adjusted by a knob, which is turned to wind the suspending thread on a horizontal axis. A scale that is circumscribed on the glass case is used to measure the torsion produced in the fiber. Let us see how Charles Augustin de Coulomb deduced the famous Coulomb's law. In order to study the intensity of the interaction force between two charged bodies, the brass disc was made to touch a small metal sphere, which was at the end of a glass rod suspended from a hole in the glass lid of the balance. Coulomb observed that the thread suspended from the needle did not move, as both the disc and the sphere are without charge. The sphere suspended from the lid of the balance was removed and charged. He placed the sphere back into the balance. The sphere and the brass disc repelled each other as the disc attained the same charge as the sphere. As a result, the needle started oscillating. The torsion angle of the thread was measured using the degree scale marked on the glass case. In order to ascertain the ratio between the interaction force and the electrical charge on the bodies, Coulomb removed the sphere suspended from the glass rod and placed in contact with another sphere of the same size. As a result, the charge of the sphere was reduced to half. The sphere was placed back into the balance. It was observed that the electric repulsion between the charged bodies was less. He then calculated the ratio between the interaction force and the electrical charge on the bodies by measuring the angle of torsion. Coulomb found that the force between 2-point charges was directly proportional to the product of magnitude of two charges and inversely proportional to the square of the distance between them. Mathematically, if two bodies carrying charges q1 and q2 are separated by a distance r, then the force is given by F is directly proportional to q1 q2. F is directly proportional to 1 by r square. F is directly proportional to q1 q2 by r square. F is equal to k into q1 q2 by r square. K is the proportionality constant called the electrostatic force constant. The value of K is equal to 1 by 4 pi epsilon naught, that is equal to 9 into 10 to the power 9. The relation F is equal to K into q1 q2 by r square is known as Coulomb's law.
Okay, so hopefully that makes sense as far as how he actually figured this out. Probably back in 1785, they didn't have a ton of time on their hands. Obviously, they're not watching TikTok and whatnot, so they can come up with these experiments that might seem obvious, but this one's a particularly involved experiment, so hopefully it makes sense how that worked out.
Coulomb's torsion.
Sorry. So, the magnitude of the electric force, this is where we're actually going to start to use some numbers, which will hopefully be exciting to you guys since a lot of this has been conceptual so far. So the magnitude of electric force, so Coulomb's law states that the magnitude of electric force is this, Fe, where Fe is the electric force, is equal to K Q1 Q2 over R squared, and it's really the magnitude of these charges. I forget exactly how it's in the reference table, but I'll be sure to mention that when I see you guys next. And R is going to be the distance between them. Sorry, I shouldn't have put that there. But R is the distance between them, so if you have charges 1 and 2, it's the distance between 1 and 2. K is the Coulomb constant, or the electrostatic constant, it's called a lot of times. It is equal to 9 times 10 to the 9 Newton meters squared per coulomb squared. Q1, this is the absolute value of the net charge on one object. And then Q2 is the same thing, except it's the magnitude of the absolute value of the net charge on the other object. And I'm not going to write all that out, but on the other object. I'm all messed up with this new toolbar over here. And then once again, R is the distance between them. So this becomes a little bit challenging. If they are just point charges that are along a line, let's say that we have Q1 here and Q2 here, that's simple, such that the distance between them would just be, this is R1, 2. We may have some problems instead, though, that let's say that we have spheres such that the objects, the charge is going to mainly reside in the center, then you would have such that you would be measuring from center to center with these if you had another positive charge here. And so this would really be the distance between 1 and 2 if this is like conducting sphere 1 and conducting sphere 2. Okay, so now that we have that all set, like I said, that has extremely strong similarity to what the Newton's law of universal gravitation. So to write it up here again, Fe is equal to K Q1 Q2 over R squared. And remember, Fg is big G M1. Oops, sorry. M1 M2 over R squared. Okay. And remember that the units of G are Newton meters squared per kilogram squared. And the units of K are Newton meters squared per coulomb squared. And remember that coulomb is the unit of charge. So you can even see that the constants themselves have very similar structure in terms of what they actually calculate out to be. So Coulomb's law is going to be used to measure the magnitude of any electric force, so remember that each object exerts the same force on each other except in opposite directions. Newton's third law applies to all forces, right? Not just friction or normal force or whatever. So third law is going to apply to everything. And since the electric force is a vector, you're going to need to specify the direction of the force whose magnitude is actually determined by Coulomb's law, and you do that by looking at the signs of both charges. So this is kind of nice in the sense that, like, gravitation was always going to be an attractive force, but now we have to consider things that can be a repulsive force between the two. But that's really just all going to be about looking at the charges, and that's why the equation takes the absolute value of these, and then basically at the end, this is how I would do it. Take the magnitudes of the charges, and then at the end say, okay, are they positive charges? Are they negative charges? Are they one positive, one negative? And from there, you'll be able to say whether or not the force was attractive or repulsive based on whether they're like charges or unlike charges. And I think personally, I think that's the easiest way to do it, just because it saves you from plugging negatives in here and possibly getting confused. So you can definitely see that they both are expressed using a similar mathematical formula where the magnitude decreases as you get further and further away as a 1 over r squared law. Again, electric force can be repulsive or attractive whereas gravitational force is always attractive. Electric force is on the order of 10 to the 36 times stronger than gravitational force. So, as far as the four fundamental forces go, that being strong nuclear, weak nuclear, electric, and gravitational, electric is the second strongest behind strong force, which is about 100 times stronger than electrical force. But just to put it into perspective, not only how strong electric force is, but just how weak gravitational force is. So when we went through dynamics last year, dynamics covered contact forces, so your normal force, your tension, your friction, okay? And law, while Newton's law applied to them, it also applies to electrical force. So is there some deeper connection between electric and contact forces? And what you could say about that is that large objects are made up of atoms, and atoms are composed of a positive nucleus that is surrounded by some circular orbit or cloud of negative electrons. So the predominant force acting between atoms is the electric force, and we'll talk in a later unit that it's really electromagnetic force is what we should be calling it. But at a macroscopic level, the predominant force still is electric force. Since there are so many atoms involved in this level, it's easier to describe these interactions in terms of non-fundamental forces such as normal, tension, and friction. But the source of contact forces is the electric force, and that's really important to remember. And we'll see a sample question about that. But remember, so normal force, tension force, and friction, those are not fundamental forces. They're because of interactions between objects. Okay. So from here on out, this is going to be a lot of examples that we end up finishing here. So a 20 microcoulomb charge is located 20 centimeters away from another 40 microcoulomb charge. What is the force on each due to each other? So if I look at this, okay, I say I have 20 microcoulombs here, and it's positive, and I have negative 40 microcoulombs here, and the distance between them is 0.2 meters, and that's important because remember K has units of Newton meters squared per coulomb squared. So everything has to be in meters and everything has to be in coulombs, and I'll change these two charges shortly here. But I'm just looking for the force, so this is a pretty straightforward question, such that Fe is equal to Kq1 Q2 over R squared. So this is 9 billion Newton meters per coulomb. Sorry, Newton meters squared per coulomb squared. The charge on object 1 is 2.0, or here we'll leave it as 20 times 10 to the 6, negative 6 rather. Sorry, I'm still waking up apparently. Because remember, micro is 10 to the negative 6 coulombs. And then I'm just going to put the magnitude once again, and then I'll take a look at whether this is an attractive or repulsive force. So 40 times 10 to the negative 6 coulombs, all divided by 0.2 meters squared. And when you do that out, you'll get 180 newtons. And so the question then becomes, and I didn't ask it here, but this is important to note that because this is a negative charge and this is a positive charge, that they would be attracted toward each other. But it's with 180 newtons. Okay. What is the distance between two charges of if they are 7.8 and 9.2 microcoulombs if they exert a force of 4.5 millinewtons on each other? So I'm trying to find distance from my Coulomb's law, which is fine. That's not a problem. I just need to rearrange. So Fe is equal to K Q1 Q2 over R squared, and I'm looking for R. So I can rearrange this, multiply by r squared here, divide by Fe, and take a square root of everything. So r is equal to the square root of kq1 q2 over the magnitude of my force here. And obviously I need to put this in newtons and I need to put these in coulombs, and I'll do that once I actually plug in. So not that I need to tell you guys this, but you could see when you were starting out in physics how putting all these numbers in multiple times would be really frustrating. So how much more convenient it is to do with variables first, but no one ever believes that until they're drowning in momentum equations, I feel like. Not for you guys, though, but I'm thinking about regions, for example. So we have 10 to the, or it's 9 times 10 to the 9 Newton meter squared per coulomb squared. That's just our electrostatic constant. And then our charges are 7.8 times 10 to the negative 6 coulombs and 9.2 times 10 to the negative 6 coulombs. That should be a C, sorry about that. Just erased way too much. I don't know what happened there. I think my line's connected. C. And then divided by 4.5 millinewtons is just 4.5 times 10 to the negative 3 newtons. And when you calculate this out, you will get a distance of 12 meters. Okay. So a 4.2 microcoulomb charge, and it's a negative 4.2 microcoulomb charge, exerts an attractive force of 1.8 millinewtons on a second charge, which is 2.4 meters away. What is the magnitude and sign of the other charge? The first thing that we're going to know is that it is attracting, and it's a negative 4.2 charge. So that means that the other charge must be positive if it's going to be an attractive force. So we say we have our Coulomb's law here. Fe is equal to kq1 q2 over r squared. And I'm looking for, let's say I'm looking for q2. It doesn't really matter between 1 and 2 which one I'm looking for. But I'll say I'm solving for q2. So q2 is equal to the magnitude of the force between them times r squared divided by k times q1. So q2 equals 1.8 times 10 to the negative 3 newtons. R, we were told they're 2.4 meters away, squared, divided by our electrostatic constant, times the charge on our known object, and I'm just going to take the magnitude once again, because all that negative is going to tell me is that they are attracting each other. So 4.2 times 10 to the negative 6 coulombs, and you will get an answer of 2.7 times 10 to the negative 7 coulombs. And once again, this is going to be a positive charge because the force between them was attractive. So this is really a charge of 0.27 microcoulombs. All right, so our next example here, we have two negatively charged objects that are repelling each other with a force of 18 millinewtons. What is the charge on each object if this distance between them is 9 centimeters? That's the first thing that we're going to solve. And the second things we're going to solve is how many extra electrons are on each object. So the number of electrons on each object, we have not necessarily talked about that yet, but it's pretty straightforward. Um, So finding the charge on each object, first of all, so we know that the charges are equal. So we can take our Coulomb's law and say Fe is equal to kq1 q2 over r squared. But if the charges are equal, it's just kq squared over r squared because q1 and q2 are equal to each other. So we could just write it like that. So if I go down here and I say, okay, Fe is equal to kq squared over r squared, I can rearrange this and say q squared is equal to Fe times r squared over k. I thought I did math wrong for a second there. Okay, we're good. So then I can take a square root of this. So q is going to be equal to the square root, and I'm going to just plug numbers in at this point, and not rewrite this again. But this is this is 18 times 10 to the negative 3 newtons. R is 9 centimeters, so that's 0.09 meters squared, divided by our electrostatic constant, which is 9 times 10 to the 9 newton meters squared per coulomb squared. And you will get an answer of 1.27 times 10 to the negative 7 coulombs. But remember, these charges are negatively charged. So this should be negative. Okay, that was a really bad negative sign here. Negative. Okay, so that's easy enough. Found the charge. So now determine how many extra electrons are on each object. So this is another equation, and this is hopefully intuitive. So the number of electrons that you have is just equal to the total charge you have divided by the charge of an electron. So remember that there's all these electrons that are making up this charge. So we should be able to calculate it in the same way that if you were to cross multiply this, that the elementary charge times the number of electrons that I have, so elementary charge times number of electrons, would be equal to the total charge that is made up here. So hopefully that equation is relatively intuitive. So I have negative 1.27 times 10 to the negative 7 coulombs divided by the elementary charge on an electron, which is 1.6 times 10 to the negative 19 coulombs. And what you end up getting is an excess of electrons of 7.9 times 10 to the 11 electrons. Okay. So that actually might be it for this lecture. I thought there was one more example for some reason, but hopefully that makes sense. We will do lots of practice on this between whether you're doing it on MCQs or MCQ Mania or FRQ Frenzy. This equation is not going to go away anytime soon, so I highly recommend that you make sure you understand how to use it.